I'd like to welcome everybody to our webinar this afternoon on the fundamentals of industrial hygiene. My name is Rich Barcum, and I will be leading the webinar today for everybody. Couple of housekeeping items, just real briefly. If you have any questions, I have everybody muted to cut down on background noise. However, if you type those in the chat box, I will make sure that I get those answered for you sometime before the end of the webinar or at the very end. With that, I'd like to go ahead and get started. And what we're going to talk about today is just really kind of what industrial hygiene is, some of the basic stuff that you might need to understand or you might need to know to take this out to your workplaces, whether you're construction, whether you're general industry, manufacturing, municipality, anything like that. So first thing is, what is industrial hygiene? In a nutshell, we have four main parts to industrial hygiene, and what we're trying to do is we're trying to anticipate, recognize, evaluate, and control workplace hazards that could cause injury or illness. One of the biggest misconceptions that we have with industrial hygiene is that it's all chemical. It's, your exposure to your silica, asbestos, lead, carbon monoxide, whatever, right? Well, the principles of industrial hygiene actually take us a little bit further than that. We start looking at biologicals, our bloodborne pathogens, our viruses, molds, stuff like that, as well as those physical hazards. And the physical hazards that fall into this industrial hygiene and role are things like noise, vibration, stuff like that actually has they're exposure elements that have a physical reaction on our bodies. And we're going to kind of touch on these a little bit. But our key factors is, we're going to evaluate our employees' exposures to those hazards. And then we're going to do what we can to control those hazards. Now, as part of this, we get into this, anticipation, recognition, and evaluation. And here is where we start getting a little bit twisted up a lot of times with our industrial hygiene programs. And the biggest reason is because you don't know what you don't know. And the thing with industrial hygiene and the thing with some of this stuff, we start talking about machine guarding or lockout, tag out. You can taste it, you can touch it, it is right there, you can see it, right? Well, a lot of these things with the industrial hygiene side of things, what happens to me today doesn't make me sick today or doesn't hurt me today. What happens today, it might be a week, might be a month, and in some cases, some of these chemicals or these contaminants, they have a latency period or a time between exposure to onset of illness or disease of up to 40 years, in the case of asbestos and mesothelioma. So that's what makes this such a unique part of the environmental health and safety field and such a unique part of our environmental health and safety program is that we're doing things now that we may never know how effective they were, except that we don't know, and we know that nobody got sick or nobody had or got hurt from it. So this industrial hygiene thing, we heard about, silica coming up, new regulation for general industry and construction for silica. We've heard about, asbestos and lead and all this stuff, right? So this industrial hygiene thing's a pretty new field, right? Well, and I think in order for us to truly appreciate something, we have to understand the history of something. So what I want to go through now is just a little bit of the history of industrial hygiene. And as a certified industrial hygienist, I like this part of it. I think it's kind of cool because it goes to show, it shows me that this stuff isn't as complex or isn't as difficult as we make it out to be, because we're going back, 400 BC, Hippocrates, father of modern medicine, right? He first noted in Greece illnesses in mercury sulfide workers. So he made that correlation between these folks are working with this chemical, and you know they have a higher incident of illnesses because of this. So you know that's industrial hygiene, that's occupational medicine, right? That's going back 400 BC. Then we get into around 1540 Paracelsus. Two reasons this gentleman right here is very important. Number one, he first started describing lung diseases in mine workers, black lung, obstructive pulmonary diseases, things like that, out of breath. So while they don't know why, they don't know the mechanisms, they're starting to understand, you know what, look, we have a thing here, and now we can start anticipating that we're going to have these outcomes from it, right? The other thing that Paracelsus did when it comes to industrial hygiene, he said something that is very important. And for those of you that have been through my OSHA 40-hour class or my hazmat technicians, you've heard me really preach on this. And what Paracelsus said was, the dose makes the poison. Everything is a contaminant. Everything is a poison. It's how much you get into your body that dictates how much of a poison that is. The example that I'm sure all of us have been touched by, heparin. Heparin, the blood thinner, right? We all know somebody, or we've had some, or ourselves, we've been on heparin that's in our blood. In a very, very, very minute dose, right? Very minute dose. It does just what it's supposed to be doing. Well, you may or may not realize that heparin is also rat poison. So you take a lot of heparin, take an overdose of it, what it's going to cause you to do is going to cause you to bleed out. So a little bit does a good thing for you. A lot of it can kill you. Let that dose make the poison. Alcohol, right? Have a beer. You may or may not have a little bit of a buzz from that. Drink a 6-pack, a 12-pack, a case, a keg, right? And so eventually, the more you get into your body, the more toxic it becomes to you. So in every little thing, this is the other thing to understand is every little thing has a different level that makes it toxic. Could take more of one thing, could take less of one thing, which is why we have very different permissible exposure limits. So I'm a big fan of Paracelsus just because he had such a huge impact, going back, hundreds of years on this field of industrial hygiene. Then we had Agricola in 1556, who wrote one of the first books on occupational hygiene called De Re Metallica. And what he did is he talked about the diseases associated with miners, and he's the first guy who actually came through and said, you know what? We can protect these folks. Ventilation, respiratory protection, things like that. Around this time, our first respirators, and we were using respirators back with chimney sweeps over in England around this time as well. And what we were using for respirators back then aren't the respirators that we know now. It's not the filtering face pieces. It's not the filter respirators. It's not that. They were using sheep's bladders. So they would dry a sheep's bladder, put her over them, and that's what the first respirator was. Get past what we're using for a respirator, and think about that though. So this industrial hygiene, and I still run across a lot of health and safety professionals who really don't know what it is, and there's really no reason for that because this stuff has been around for centuries. Now, the difference between then and now is we know a lot more. Our technology is a lot more advanced. Our methods that we can detect are more refined, but the principles are still there. Around 1700, we have Ramazzini. He's the father of industrial medicine. Okay, in a little bit, I'm going to talk to you about the mother of industrial occupational medicine. Okay. The father of industrial medicine, he wrote an article that was, or a book called De Morbis Artefactum Diatribum, And what that is the first really good hard study of various industrial diseases. Now, where he came into play is he expanded on what Hippocrates had as far as a medical history, and he asked the question, what is your occupation? What do you do for a living? So again, we're still taking these and we're making that leap between what do we do in the workplace, how it affects us outside of the workplace. Some additional, in the late 1700s, 1800s, we had a lot of urbanization, industrialization. 1858, gentleman over in England had the first charcoal-based impregnated mask to control gases and vapors. Before, the respirators were particulate. Now we have a respirator that's coming up that's going to start filtering out some of those gases, vapors, some of those other toxics, right? Well, again, we're getting more advanced on what our control methods are. In 1889, we started seeing studies in the UK as far as they're going to set some exposure limits for humidity, carbon dioxide in some cotton mills. So we're kind of progressing through here. 1890s, Haldane undertook some work to study the toxicity of carbon monoxide. This is where we started really getting into the time versus dose discussions when it comes to industrial hygiene. Because remember earlier, Paracelsus said the dose makes the poison, right? So it's how much. Well, now what we're showing is how much over time. And this is where we start moving away from acute to chronic. Whereas, and so we start really starting to understand that if I get a lot right now, I'm dead. If I get a little bit over a long period of time, same result. So we're starting to really understand that, and we've all heard about the canaries in the mines. This is our boy right here. He's the one who introduced that into the mining industry to give levels of toxicity. So I always thought that's pretty interesting because we always hear about that canary in the mines as a method to tell if the air was not toxic. So here's our boy right here. 1910, the mother of occupational hygiene, Alice Hamilton, really started pioneering some work between toxicology, industrial hygiene, between exposures in the workplace to industrial diseases, and where she really started coming in and started making some headway is in the field of lead exposure. She's one of the first ones that really kind of tied that together. Move on here. 1920s and 30s, industrial hygiene started growing a little bit. ACGIH in 38, 39. In the 70s, we had OSHA. And even today, we're still furthering this. So it's important that you guys understand that you might seem a little bit silly to talk about what the history is, right? But to me, when I understand the history, it takes away some of the myth of what some of this stuff is really about. Because I'd say less than 2 out of 10 people, 1 out of 5 people that I would ever talk to said they actually enjoyed chemistry. And just a natural human reaction is if we don't enjoy something, we tend to steer clear of it. If we don't understand something, we tend to steer clear of it. And that's what I see with industrial hygiene is, so what I want to do with this history is just kind of show everybody, you know what, look, we've been doing this for decades, for hundreds of years. It's not that mysterious. It's just a matter of understanding what it is on a very macro level, on a very big level. Why is it important? Every day, according to the Bureau of Labor Statistics, or NIOSH, average of 9,000 workers suffers disabling injuries on the job. 137 workers per day die from a work-related disease. Think about that. That's a pretty big morbidity rate when you think about it. And a lot of times, they don't even realize what they're dying from is work-related. We don't understand the roles back up. industrial hygiene profession, EH&S profession. We understand the roles, okay? What we don't understand is how to communicate that to our workers so they are educated, so they understand. So as a society, as a working society, we still don't really understand what's going on over here and on one side of the facility, what's going on in my workplace and how it affects me big picture, long term. On-the-job injuries cost about $156 million or $1 billion in 2003. That number's gone up. 78 million of that was, or $1 billion of that was wages. Liberty Mutual did a research study that said nearly for every dollar invested in safety, a company saves between $3 and $6. Okay, and what that is I spend a little bit now on my air monitoring, on my evaluation, my anticipation, my recognition, and my control. What I do is I save quality of life for my workers. I save morbidity of my workers. They're happier, they're healthier, which means they don't go looking for other jobs. So I don't lose the investment in my workers. So this is kind of why industrial hygiene is so important. Okay, and again, just some additional statistics. World Health Organization, which is global. 386 deaths each year from airborne particulate. That's asbestos, lead, silica, cotton dust, coal dust, all that stuff. About 152,000 deaths per year from the workplace just from carcinogens. Okay, cancer causes. And then the bottom one, 37% of low back pain is attributed to occupation. So for those of us that have low back pain, almost 40% of us, we can attribute that to work. And again, understanding this industrial hygiene doesn't necessarily mean you're working in a factory or you're bent over. It could just be that you're sitting in a really sucky chair for years and it causes low back pain. So that's kind of the big picture. Why is it important? And then just kind of give you an idea, about 228 people worldwide have died in the last hour from a work-related illness or injury. So kind of let that one sit there for a second and just kind of think about that. So that's where we've come from with industrial hygiene. That's why this has become so important. Been doing health and safety for almost 30 years. And I'm telling you, this is still the most widely misunderstood part of health and safety that I run across. We don't understand the chemical exposures. We don't even understand what the exposures are. And one of the problems with that is we rely heavily on safety data sheets. Safety data sheets are not the end-all, be-all. They don't tell us the full story because when you go back to the dose makes the poison, and that dose, the dose versus time relationship, what that safety data sheet doesn't do is it doesn't tell me how I'm working with it. It doesn't tell me where my head is in proximity to whatever is being generated. It doesn't tell me what controls are in place, such as respiratory protection, such as ventilation, anything like that. So we really don't understand big picture. And I'll give you an example of what I'm talking about there. If anybody's ever done PVC pipe, PVC pipe, you use that primer and that glue that, you're standing out in your yard and you can get a contact high off of just working out in your yard on a windy day, right? But you take that same material, do the exact same work, do it in a crawl space. And then you take that same material and you do it in a bathroom. And you take that same stuff and you do it in a half bath. So we're increasing dose. So that's kind of where I'm driving with this, is we just still a large misunderstanding. So steps to protect our employees. Number one, coming back to anticipate, recognize, evaluate, and control. So how do we anticipate our hazards? we have to know what's in our workplace, right? We have to know what chemicals we work with. We have to know where our environmental extremes are. We have to be educated enough to know how to look for that stuff. And the folks that work with me here at Cardinal, they've heard me say this a lot. We can't overlook anything. We go into a facility and they have a wash rack, not electroplate. It's a wash rack. Well, what are we using? What chemical are they using? Well, you're using water with some detergent. Okay, what type of detergent? Because we take the wrong thing and we put it under the wrong circumstances in the wrong area. It can potentially be life-threatening or cause long-term illness. Once we anticipate, okay, we're dealing with this stuff, then we have to recognize and evaluate where our real concerns are. Okay? The way that we do that is we do our research. We recognize that, okay, chemical A, based on safety data sheet versus in the literature and information from the manufacturer, has a lot higher toxicity than chemical B. And so we have to do our homework, and that's how we recognize where our serious issues are coming from. Okay? The other part that goes with that recognition that gets missed a lot is we have to talk to our workers. Now, I know the folks are saying on here are saying, you know what, I really don't like talking to people. But that's the only way. That is the only way, because when we go out, we start talking with people. I go out and I talk with Zach, and I say, hey, Zach, how you feeling? Oh, well, you know, I go home every night, and I have this blaring headache. I just feel like I'm getting sick, but waking up the next morning, I'm feeling good. Okay, well, what does that do for a living? Remember, Ramazine, what is your occupation? Well, I talk with Zach, and I find out that Zach's welding about 4 to 6 hours a day. And I'm a good industrial hygienist, so I do my research, and I was like, with welders, there's this thing called metal fume fever. That's a transient thing. It's a non-life-threatening illness, but it's a thing where, you know what, you get exposed to these metal fumes, it presents itself as flu-like symptoms. And pull you away from that exposure, guess what happens? That stuff metabolizes out of your body. You're feeling good the next morning. So in this case, where I see a lot of times like, well, yeah, it's just, I understand he's exposed to this stuff, but everything I've read has said that, well, you know what, it's not a big deal. It's not going to cause any issue. He's right. Metal fume fever doesn't cause any issue. But when we start getting into recognition and evaluation, what that's telling me also is that you are definitely getting something into your system. So then we start driving down a step further. Lead, cadmium, manganese, antimony, zinc. Are you welding on galvanized steel, hexavalent chromium? So you start getting into all of that stuff. And this is where we start this industrial hygiene stuff. This is where you kind of got to put your top hat on, your investigator hat, and start digging in and looking at some of this stuff and understanding what the true hazards are. Okay? And then we're going to evaluate. How do we evaluate? There is only one surefire way to evaluate, and we have to put the science behind what we think we already know. Okay? Look, I can walk into your facility, and I just dealt with this with a client, and we're doing a job for the Army Corps of Engineers, and the client did not want to do noise monitoring. Because they did their homework. They were working with a Metabo grinder. They found the manufacturer's data, right? And it said that one Metabo is about 93 decibels. Well, they're only going to be doing it for a couple hours a day. So they did their homework, right? And they said, well, how about this? How about we just put our people in hearing protection? And that way we don't have to worry about it. And because they know, and I agree with them, they know 100% that putting their people in earmuffs or earplugs in this case is going to protect their workers. I have zero doubt about that. Well, the client, the Army Corps, is absolutely right when they say, but how do you know? You don't know until you do Okay, so that is the only way. So what I tell people, and this is how I practice industrial hygiene, is that, yep, you're right, you know. But how do you know? Well, I just know. Well, how do you know? Well, I just know. You're not hearing me. How do you know? Well, I guess I don't. There you go. The only time I can use what's up, that lump that's, about 3 foot above my rear end, right, on my head, the only time I can use that is when I have science in the past that has backed it up. There is a difference between somebody who is working in a factory and you've done no air monitoring, trying to say, well, but I know, without doing air monitoring, versus somebody like myself who has worked in that industry. I've taken samples before. I've seen a large, number of different types of jobs under these circumstances. So I can use some of that knowledge. So I'm not saying you can never use that baseline knowledge, what you guys know. What I'm telling you is you got to have some data to back that up, if that makes sense. So you always, in order for me to evaluate, you always have to have the science to back up what we already believe, okay? Then we're going to come down to, once we know we have a problem, we're going to come down and we're going to start looking at protecting our workers. So we want to control that hazard. And what we're going to do, there's a variety of different ways to protect our workers, and there's a hierarchy of control, okay? And we're going to add, for most of us, there's, PPE, administrative and work practice, and engineering control. With industrial hygiene, I'm going to add one, substitution. So starting at the top of our pyramid, we're going to work down is how we want to do things, right? Because the higher up we go, the more effective they are. I have chemical methyl ethyl death, okay? It's just highly toxic, okay? I look at it and I die, all right? But there's, so I have that, and with this, I'm going to have air supply respirator. I'm going to have some, state-of-the-art ventilation systems. I'm not saying we can't work with it, but there's a lot of stuff we have to do, right? Which is going to slow down productivity, which is going to cost me money. Or I have a chemical base that is not quite as effective as methyl ethyl death over here, but it's pretty good. It gives me what I need from it, right? But I don't have to go through all this other stuff, right? So I no longer have a potential for that exposure. Not only am I removing the hazard, I'm just taking it completely out of the equation. So there's no way I'm going to get hurt if it's not there. The next step is my engineering control. That's things like ventilation, stuff like that. And the idea behind ventilation is I prevent the hazard from contacting my worker. Okay, I take it out. My engineering control for safety would be like machine guarding, stuff like that. We're talking ventilation, we're talking welding curtains, stuff like that, right? To prevent that hazard from actually contacting my work. I'm kind of putting a barrier there. Then we come down to administrative and work practices. The reason these start becoming less effective is because I start relying on people. Okay? And people are going to fail me. People are going to forget. People aren't going to care. People are going to have a bad day. So these administrative controls are, I need to limit the amount of time that you are exposed to something because I have permissible exposure limits. So what I'm doing is I'm putting up a barrier that you're not allowed to go in here. Or I'm going to change how you work with something to prevent exposure, okay? And then my last line of defense is my protective equipment. That's my respirators and gloves and stuff like that, okay? And the idea behind why that's the least effective is because I am still there, exposed to that hazard. I'm just putting a barrier between myself and that hazard. Okay. Here's a mistake I see get made. We hone in on one. I see two mistakes. Number one is we go right for PPE. Okay, and that's a mistake. Number two, that's a mistake for a couple of reasons. One is it's not the most effective. Number two, OSHA is going to require you to do some type of at least look at engineering controls. Most of our regulations come out with engineering controls as feasible, and feasible ends up, money comes into that equation. But they want you to at least look at engineering controls. And then the other piece of it is we tend to hone in on one without looking at all the others. So when I'm talking about protecting you, I'm looking at, when we're talking about this hierarchy of controls, I'm looking at all of them in conjunction with each other. And I'll give you an example. One of my first jobs right out of college, I worked at Idaho National Engineering Lab for the Department of Energy. And then right immediately after that, I worked for Rocky Flats out in Colorado. Rocky Flats used to make the nuclear triggers for weapons. Okay, so it's very, very high hazard environment. Things like sulfuric acid mixed with plutonium type stuff. We had a few activities there at Rocky Flats where we had to use all these. I had to protect my workers, right? But with radiation, you have an annual dose that you could be exposed to. We had a couple of jobs where we'd have somebody in there for an hour. They would use up their entire annual dose. We'd have to bring them out, bring somebody else in. And that's an 8-hour job. You think about that, but that's the only way to get that job done. We had them protected. We had our engineering controls in place. We had them shielded the best we could, but we also had to pull those work practices, administrative controls in to make sure that we are protecting our workers. Now, in this case, they could have actually been exposed for twice that long, but we halved it. They signed a release. They were cool with it. They knew what they were doing, because it got them out of some really crappy assignments for the next, 364 days. But that's how all that works together. And in order for us to do, remember, this is the fundamentals of industrial hygiene talk. That is one of the fundamentals, the basic tenets, is we have to look at all of these things and understand how they all work together to adequately protect our workers. So, what I have here, I have a list of different occupational / exposure limits, okay? As an industrial hygienist, we play with all of these. What I'm going to focus on, the top 4 and the bottom one. Time-weighted average, TWA. What that is I am not always looking at something in the terms of the here and now. I'm looking at it in terms of big picture. Because we know what these levels are, kind of an average. It's kind of like, you take a trip, you drive to New Orleans, right? And you're checking your gas mileage. And you check your gas mileage and you're getting 22 miles per gallon. Does that mean you are consistently getting 22 miles per gallon in your car? Well, it's an average, right? And sometimes you're better than that, sometimes you're less than that, depends on traffic, depends on a lot of different stuff, right? That's what my time-weighted average is. Okay? So we start talking about these occupational limits, that's really what we are talking about. Okay? These those time-weighted averages. So what I have is I have a few different ones, okay? And I have a few different organizations. Number one is I have OSHA. OSHA sets my permissible exposure limits. Okay, that's the law. But I also have the ACGIH, which is the American Conference of Government Industrial Hygiene. And I also have NIOSH, National Institute for Occupational Safety and Health. They all three do different things, but they are all very important. OSHA sets my law. ACGIH does research on a regular basis. That is a recommended level. Okay, that is an industry based on literature, based on research, what they think the best permissible or the best limit is, okay? You have NIOSH, and NIOSH is actually an arm of the Center for Disease Control. They're part of the federal government. ACGIH is not. NIOSH is not a regulatory body. Again, they are a guideline type of thing, okay? So I'm going to talk to you about what the differences of these are. Number one, OSHA have a permissible exposure limit. It's an 8-hour time-weighted average. But we have to understand what that means. My permissible exposure limit and my threshold limit values are both 8-hour time-weighted averages. The amount that a worker can be exposed to, 8 hours a day, 5 days a week, for 40 years. 40 years. And the reason I bring that up to make sure that you guys understand that is I see too often, I see a company that gets an exposure above the permissible exposure limit, barely above it, and they have a bunch of knee-jerk reactions and they overreact because, oh, we can't go over the PEL. Well, you're right, you shouldn't go over the PEL. But from a practical standpoint, that is not something to always get excited about, okay? That's the equivalent of me pulling the fire alarm for a trash can fire, okay? So my PEL and my threshold limit value are both 8-hour time-weighted averages, 8 hours a day, 5 days a week, 40 years, all right? But why does ACGIH and their threshold limit values even exist? What are they there for? Well, the problem is my permissible exposure limits. Back in 1987, OSHA tried to come through and do a wide-ranging, sweeping change of my permissible exposure limits, and I'll talk about where those are here in a second. Congress came back, got it down, and said, nope, because we have lobbyists, we have big business, we have other interested parties, right? They came back and they took us to court, and Congress repealed the law. They said OSHA didn't do their due diligence. Didn't do a good costing analysis, all that stuff, okay? So a lot of the permissible exposure limits that we see in 1910.1000 Table Z, Z is in zebra, go back to the 1968 data from the American Conference of Government Industrial Hygienists. A lot of them do. Now, we've had some that have changed, silica, asbestos, lead, hexachrome, but they're cadmium, but they're changing those on a contaminant by contaminant basis. That's how they're having to go through and do it. But that's why I talk to you guys about what that definition of a permissible exposure limit is. But here's the deal. Even if it's 1968 data, I'm talking, this is industrial hygiene for the everyday person, right? Even if it's 1968 data, and they say that I can't be exposed above this level, you got to keep in the back of your mind. I'm not saying you don't react to it. I'm not saying you don't take steps. But you got to keep in the back of your mind 8 hours a day, 5 days a week, for 40. What are the odds of that? And the reason I point that out, because this is kind of a, guess what's the word I'm looking for? Kind of a side note here. One of the biggest mistakes that I see EH&S professionals make is that they don't understand the hazards. They overreact as if everything is a catastrophe. Everything has to be fixed right now. And so I think if you really understand that, and that's why when we start talking about, and I'm going to get into some of these other limits here because it's very important. That's why we get our programs get derailed, and we see industrial hygienists get a bad rap because they just don't get it. And you know what? They don't, because they don't really understand their own profession. NIOSH recommended exposure limits. Those are based on not on an 8-hour time-weighted average. Those are based on a 10-hour time-weighted average. OSHA is a law. Those change as the law changes, right? ACGIH republishes about every 2 years. They're constantly looking at everything about every 2 years. And then if you guys decide you want to sit through the 4-hour class of this, we get into some of the biological monitoring and stuff like that the ACGIH kind of pushes. And then NIOSH is about every 5 years they republish. So kind of give you an idea of what the different guidelines are, okay? They all have a STEL, or a short-term exposure limit. Short-term exposure limit is the amount that I can be exposed to for 15 minutes, 4 times a day, with at least 1 hour in between each exposure. Okay? 15 minutes a day, 4 times a day, with at least 1 hour in between each exposure. Okay? My ceiling limit is the amount that I cannot go over. Okay, that's mine. I get exposed, I have immediate potential health effects. Okay, that is a 5-minute exposure limit. Okay, 5 minutes. I have the skin notation, which is skin notation. If we see that with a chemical, what that says is that absorption through the skin plays a role in my occupational exposure. Asbestos, look, it's all airborne. If you get asbestos on my skin, I wipe it off. No harm, no foul. Okay. And then I have IDLH. IDLH is the level that I can be exposed to for up to 30 minutes and still be able to self-rescue. It's exposed to 30 minutes and still get myself out on my own. You have to understand what these limits are. IDLH does not mean, oh, I died. It could, but you have to understand. You have to understand this stuff. You have to understand where your permissible exposure limits are. Use oxygen in confined spaces as a good example. 19.5% to 23.5%. Below 19.5% is considered IDLH. You know what though? 16%, I start having labored breathing. Look at myself now. 7%. Yeah, I'm going to start going into convulsions. I'm going to lose consciousness, things like that. So again, the way I teach on this is, look, you're at 19.5%. That's my limit. You're at 19%. Don't panic. Only get yourself out. You're at 9 or 10%. Run. Okay, so that's kind of how you have to look at this, and it's for any chemical. For example, lead. 50 micrograms per cubic meter is my permissible exposure limit. My action level is 30 micrograms per cubic meter. If I'm at 55 one day, I'm not going to get bent out of shape. We're going to take a look at it. We're going to investigate. We're going to look at it. Not a big deal, right? Because I know that you're not going to be exposed to that level for every day for 40 years. It just doesn't work that way. Now, if you're at 200, I'm going to get a little freaked out if you're not protected. So that's kind of how you kind of prioritize and trying to help understand this stuff. And what I found in my career is when I react appropriately to things, to hazards, I get a lot more credence. I get a lot more credibility. So that when I do have to overreact in somebody's opinion, they know to listen to me in those situations. Different air contaminants that we might run across. You got dust, fumes, mists, vapors, fibers, and gases, and they are all different. Welding fumes, asbestos, lead, hexchromes, silica, carbon monoxide, carbon dioxide, acid fumes, you name it. And anything can be toxic in the right quantities. Got my biological hazards. That's my bacteria, my viruses, my fungus, my molds, my black mold. And it's understanding how do I determine whether or not something is a hazardous species of mold. I know we should all, this is where, all mold's hazardous, right? Oh, no, not necessarily. They all react differently. We have our physical hazards. We have electromagnetic radiation, noise, vibration, temperature, illumination. And people ask me, well, how these aren't physical? How does this fall into? I want you guys to think about any time where you have been, let's see here, anybody got kids? and or dogs, okay? And you get the kids over for Christmas, and they're all under, got four kids or grandkids, all under the age of 5 on Christmas morning. I want you to ask yourself, after all the presents are opened up, how much fun did you have? How do you feel? You put yourself into a high noise, high stress environment, it has physical effects on you. That's why when you're in a high noise area for a prolonged period of time, that's why you start getting irritated, start getting angry, start getting antsy, you start getting jumpy. And what effect that has on safety is you're not focused on what you need to be doing. To me, this is the whole premise behind don't make me turn the car around and go home, right? That's a safety thing. So if anybody gets in trouble for saying that, that is a safety thing. You're trying not to wreck the car. So those are our physical hazards. We have ergonomic hazards such as eye strain, repetitive motion injuries. That's our carpal tunnel, lifting injuries, stuff like that. Okay. Then how do we measure contaminants? So that's when we start getting into putting the science behind what we need to do, okay? Variety of different ways. There's 2 things that we're going to do. We can do air monitoring or air sampling. Air monitoring is like taking a picture, okay? That's what I know is happening at this moment. Air sampling is like me taking video, giving me a longer, big picture. Okay, this is what happened over this period of time, okay? For air monitoring, I got, gas meters, my 4 gas meters, my photoionization detector. It could be a Jerome meter for mercury. It could be a benzene monitor. It could be a variety of different stuff, okay? Just a couple of examples. And these are going to give me a quantifiable or a hard number. This is what you have in the environment right at this moment, okay? Either for a specific chemical or a range of chemicals. Then I have my bellows pump or my piston pump. And what that is my calorimetric or my stain tubes. Okay, these are considered qualitative measuring devices, okay? Because what they do is I draw air through a bellows pump that comes into a tube that has some different chemicals in it, and the idea is whatever's in the tube reacts with what's in the environment, and it gives me an idea, okay? But there's a lot of different errors that can come through here, okay? And what I'm looking for with my industrial hygiene is I'm looking for what's called a confidence level. I'm looking for a confidence level plus or minus 5%. So around 95% confidence level is what I want to have in my monitoring. Okay? And there's a variety of different ways for me to get that confidence. And it's too much to talk about in this particular webinar. Then I have air sampling. I have personnel sampling. I have area sampling. I have or 2 types that I can do, either integrated or composite sampling. That's where I have a pump that hooks to a tie-down tubing or hooks to a rubber tubing that hooks to a filter or some type of sampling media, and I'm drawing air through it through the breathing zone of my employees. Or I have what's called passive dosimetry, which is just a badge that you open up and you let exposed to the air, things like formaldehyde badges and stuff like that. They're both good. It really depends on what is required and what method you're going to use, because that is something that's very, very important. Is when we start looking at sampling, and this is where I see mistakes made a lot. Okay, you don't understand what sampling entails for a particular chemical, okay? And I have a theory about why this is, because it seems to me that every time I run across sampling, I've got to do it at 2 liters per minute. Everything's at 2 liters per minute. Well, the reason for this, we do more asbestos sampling than any other type of sampling in industrial, things like that. You're constant, because there's some regulations that mandate it, right? And asbestos sampling is done at 2 liters per minute. But that's not always the case. Some NIOSH methods or OSHA methods which is NIOSH, National Institute for Occupational Safety and Health, has a book called the Analytical Methods, manual, that tells me how to collect samples, what my filter media needs to be. Is it a sorbent tube, or is it a PVC filter? Is it a mixed cellulose ester filter? Is it open cowl? Is it closed? It tells me a bunch of stuff, okay? Because there's certain things that I need to do in order to increase my accuracy of my sample, okay? And they're also going to tell me what volume, what airflow, and then at what volume, and that becomes important, because if I don't draw enough air, if I draw too much air through my filter or my collection media in a highly contaminated area, I oversaturate it. I oversaturate it, I can't read my sample, it voids it, right? It's just too much there for me to get an accurate reading. If I don't draw enough air through it, okay? With these analytical methods, there's this thing called the limit of quantification, or the limit of detection, okay? And that's the bottom line. That's the best that my method can do. What most people don't understand is that the more air I draw through that sample, the more I drive down that limit of detection, which makes my data a lot more accurate. So a lot of these analytical methods will give me an air volume between this much air and this much air, between this many liters per minute and this many liters per minute. So I know this is going to break everybody's heart, but you have to do math. You have to figure that out, because what I've run into, especially for lead, have people do a 30-minute sample on lead, and it'll come back, and you never get zeros with your analytical methods. You always get less than. So the best you're going to do is less than limit of detection. So if my limit of detection is 30, and my data says less than limit of detection, or less than 30, my number's 30. And that's my worst case scenario. But what I've seen, what I've run across before, and particularly with lead, is we have a limit of detection of 70. And my data says less than 70 micrograms per cubic meter. Hey, we don't have anything, right? Nope. You have 70. My permissible low exposure limit is 50. So if you don't draw enough air, you kind of shoot yourself in the foot by not driving that limit of detection down. That's a hard thing for people to understand. Is the importance of that. Then I mentioned cyclone. Cyclone it filters out the big pieces. It kind of we start getting into respirable versus non-respirable particulate, and then calibration. How do I calibrate? What do I use to calibrate? If I'm using a rotometer, has that rotometer been calibrated to a primary standard? A lot of different things that go on there, and all of those need to be in play to make sure that I drive down or drive up my accuracy, okay? If I don't get that 95%, unless I'm really low, that's hard. And there's a lot of other things that come into play with this is, how do I sample? And all these different pieces. And everything that I have listed up here is a potential source of an error in my sample. And then it's how many samples. Can I replicate those samples? A lot of different stuff that kind of comes into play to get my accuracy up to where it needs to be. The other piece here that we can look at is, or that we would look at, is how do I use the data versus how OSHA would use the data. And there's some tricks there that we can use to fight OSHA on chemical exposure that most people truly don't understand, and has to do with that upper and lower confidence level. Has to do with that 95, that that confidence level plus or minus 5%. Okay. So again, why is this important? Just explain some, what we're going to call people behind the numbers, right? Behind why it's so important. This is Johnny with a pipe fitter at a steel manufacturing plant where an explosion occurred. They had warned about combustible hazards for years. Nothing was done. 6 people died as a result of not having proper industrial hygiene programs. An example of Lewis Harrell displays his plaque recognizing his loyal and faithful service to his employee as he died from lung disease from a cotton plant, cotton processing. Mickey was a welder, welding on some tanks of petroleum, did not do proper air monitoring, industrial hygiene, right? Proper air monitoring, caused a fire, caused an explosion. Mickey was on fire, found dead. She later died after reaching the hospital. That's the truck. Okay? So that's why we do this stuff, and we think that it can't happen to us, and we think that I don't see it, therefore it must not be there. Okay? The industrial hygiene profession is like a kid. And as a kid, we've all said this, as we get older and we mature, we've all said this. Young kids just don't realize their own mortality. They don't realize that it can happen to them. We've all said that or heard that, right? This is the same thing. Well, we don't see it, it must not be there. And this is why this industrial hygiene stuff is so hard to get across to people. Because, number one, it's not understood. Number two, we can't see it. We can't point to it. We can't show it to somebody. All we can do is talk about in hypotheticals and potentials, right? So with that, that is what I have for our overview on fundamentals of IH. If you have any questions, and I don't see any questions right now, but you can always get a hold of me at Cardinal, 419-882-9224, or by emailing me at rich@cardinalhs.net. But I do want to point out we do have some additional webinars and some open enrollment classes. We're doing a fundamentals of IH, the full course on July 11th out at Northwest State. It's a really good course. We deep dive into some of this stuff, talk about how to do some of these calculations, how to do some of the math, and just more well-rounded approach to this topic. So if you're interested, you can go to our website, www.cardinalhs.net, find out about that. And then you see the webinars. Please sign up. Love to have you guys. And with that, I'm going to close out. Thank you all very much. Have a great day.